Okay, so today we're going to be going over assignment 2. For this assignment, we actually had to import a couple of libraries. Some libraries that we had to use. Specifically, we had to use PyTorch, since that's the common practice nowadays instead of using TensorFlow. So, in order to do that, we just import it as such. Just import torch. And these are a couple of packages that we've used. So we did have to import something called pickle. That just helps us like loads and like save like binary data, like the CIFAR 100 data set. And then we had to import some PyTorch. PyTorch, basically it's a library used for deep learning. More specifically, this .nn is for neural network components. So that's why we're using it, because we're going to be dealing with layers, activations, and some actual loss functions. Iterative tool, that's a new one for us. So that one we just use to help generate like all the possible combinations of the hyperparameters. Okay, so we have quite a few functions here, and how it works is that I'll explain what this each function do, and then that way, and here is actually where the action's happening of when we're calling them and actively using it. So essentially, for this first function we call load database, the aim of this is simply just to load the data. It was a bit tricky in a sense that we had to open this data set for training and testing and stored it as this binary data, as to, because we had to use pickle files, so we're pickling or unpickling the files. And the aim of this essentially just to extract image data. Image data is the X train and the X test. That's image data. Labels, though, are the Y train and Y test, and then we're returning these values. So we're opening it, forming a train dictionary, opening the test, forming a test dictionary, and then we're extracting the binary data from the train dictionary and storing into train. Same thing with the T for test or X test, and then for Y train and Y test, same thing, except we're converting those into the NumPy array. Now, a good practice is to pre-process your data before even training the model, and so here that's what we aimed to do. So you'll notice here for the X train and test, we did have it divided by 255, and that's not a random number. We find that pixels values range between 0 to 225 or 255, and so we want to normalize the image pixel values to 0 and 1 range. So I just divided by 255 for the X train and X test. But for the Y, the labels essentially, we had to make sure that they have an integer class label for both the train and test, because it was causing some problems when we didn't do that. So I went ahead and used torch tensor for that to ensure that they do have the correct labels and they are integer class, and I returned that. So that's pre-processing the data. And now this, what I'm about to talk about, is a class, and this class is called MLP. MLP stands for multi-layer perceptron model, which is basically a neural network. And this class, the aim of it is just to define this neural network, and this neural network has 5 hidden layers, and I'll show you. This is the hidden layers I'm referring to right here. And so this model, it accepts the input size, and I believe the input size is about 3072 I have it called here. Here's where we're initializing it. So the input size is 3072 pixels for that data set. Okay, so this is the default constructor right here in the init. So once it's being initialized, this automatically gets run. And so this is where we are setting the input size, units, hidden activation, output activation. So our activations are these two options, ReLU, sorry if I'm not pronouncing it right, and the sigmoid. And the output activation, softmax, and then another type of output activation is sigmoid. And here are our 5 layers. Okay, and then so on this last layer here, this line essentially is 64. We are just want to make sure that the selected output is being applied to the activation layer, and it is. So this function here, it's called forward. Now forward is an important function in the fact that it just describes how our data is flowing through the neural network. And this is the reason why it's called forward is because we're using something called forward pass. So essentially with this, we have to pass itself and x. And what line 67 just does is that self.layers is just, think of it like a sequence of layers that helps just define our init method right here. And we had to use the dot sequential, right? And so the X just represents like the image data that passes through a connected layer of neural networks and the activation function. So essentially what we're returning here is the last activation layer. So as basically after passing through all the layers, the X in this case is processed by all the output activation function, which could either be a soft max or a sigmoid. And yeah, so that's what that does. So I'm just gonna close this class here. Okay, so now let's go talk about training and evaluating. So to train this this model, it was asked of us to make sure the epoch was set to 200, and so that's what this does. Essentially, we are looping through each epoch, and we're training the model, and we're giving the images and label. Yeah, so let's see here. So the train like underscore loader, that just aims to it's just essentially like a data loader, and that data loader just helps like load the training data in batches. So that's what the the train loader aims to do. And so the aim of this is basically just to loop through each epoch, so over many batches of the images and even labels from the train loader. So that's why we're including the train loader. And so with each iteration, the new batch of the training images are corresponding to their labels, which helps with the training. So essentially, that's what this does right here. And so this I had to include because since we do have two types of loss functions, if it was, the MSE loss, then what we want to do is make sure it's an instance of that, and if it is, then make sure that we're using one hot encoded for those labels because the cross entropy doesn't need that. And so this line right here, 82, we have a variable called loss, and it just helps us calculate the loss for each image. And then line 83 is using backwards propagation. line 84, actually 85, dot step just updates those weights. So that's it for the most part for the training, and now this is kind of the evaluating part. So we just evaluate the model after we break out of the loop, and then then we're using the test loader, and we're extracting the predictions class and making sure it matches the label, and then adding it to then just keep track of the number of part that it was accurately predicting it correctly. And then afterwards, we basically calculate the accuracy of that model by dividing the correct over the total, and it returns the accuracy. And so the trained model, well, what it aims to do is to return the accuracy. So I'm going to close this guy. So this is the P. This is what in the directions it had this hyperparameter grid search. So we just brought it over here. Now we're actually calling some functions. So we're going to load the database into each of these variables, and we're going to pre-process these variables, and then we're going to relabel them or reassign them to its respective value. Then we're just converting them into PyTorch sensors. Okay, so now this is kind of where the magic happens, in a sense that we're actually going to perform the hyperparameters grid search. So we're just going to have an empty array called results, and at the end we're going to append an object into this and display it. So to do that, we have something called all combinations. So for this aspect, the aim of it is just to essentially compute something called the Cartesian product, and what that is just contains like all the possible combinations of the p dot values. So essentially, this little star operator, it basically helps like unpack those the dictionary values, and we can pass them as separate arguments. So that's like a neat little Python hack that we could do there. So essentially, we are going to, um, we're going to generate every possible combination for the hyperparameters, and then store the results in a list. And reason why we're doing this is because we want to generate all hyperparameter combination, and to that we're using the Cartesian product, and so we're storing those combination as tulips, which is just a tip, basically a list, and then we're going to use the hyperparameters tuning in the training loop, which is why we're calling the training model here. So we're going to go through each combination, and in this param dictionary, we're going to form a dictionary of the p keys, and then the values be the parameters. And then we're going to actually do the data loader. Remember, we had to do these mini batches because there's a lot of data to go through. And we're going to call on the tensor data set for that help. Then this model just serves to initialize the MLP, and that was really necessary because we need to create the neural network. So we're calling that class, and we're passing in the input size and the units, the hidden activation, the output activation. You'll notice it's basically what's the results, key value pairs. So then we set the epoch to be 200, since that's what the directions required. And then finally, for this part, we're basically just going to be looping through each of the hyperparameter combinations. So as I mentioned, we did some initialization. It goes through, and we were left here. So if we kind of look back, there's actually 64 combinations, because there's 2 types for each one. So there's 1, 2, 3, 4, 5, 6, 7. So it's like 2 times 7. It's like 2 times 2 times 2 times up to like 7 iterations of 2s. And that comes out to be 64. And so essentially we're checking for each one. Check what kind of loss function are we having. Are we doing MSE or are we doing the cross entropy loss? If it's MSE, go in here. Take the processed, we're going to create a new, first of all, we're going to take a criterion. It's going to be using the MSE loss function, using that library. Then we're going to be using the process Y train and the process Y test, and we're going to do the one hot code to that because, again, MSE requires that, but guess what? Cross entropy does not. So we can just reassign the Y train into process Y train and then Y test to process Y test. But for MSE, it's different. You need the one hot code. At least I need it in my case. Again, when we were iterating, we have two different types of optimizers. There's an atom and ADA grade optimizer. And so if it's atom, we want to call into this function atom and pass in the model's parameters. But if it's an ADA grid, then you just pass in those parameters. And then we're going to store the accuracy by calling on the train model function that we've defined earlier, passing these parameters in to calculate the accuracy, because remember that's what the train model does, it returns an accuracy. And then we're storing all those results into this results object, and we're going to store it into this empty array called results. And I just want to point out for the accuracy, we multiply 100 because I want to get in a percentage format, and then it outputs the CSV file called results, and this is what it looks like. And I said just go ahead and print done when you're done with it. And so this is what it looks like. As you can see, there's 64 outputs. One of them is considered the title, so 65 minus 1 is 64. There's 64 combinations here. And the highest accuracy, or at least just the very first one, the accuracy, it's 32. So that meets that criteria. And these are the different types of combination. So in all, you just wanted to know, like, the point of this is just to find what was the best model just when running this. So we basically, train an MLP on using this specific data called CIFAR 100 data set. And we're just using the grid search to find the best possible model. And we can look through here in terms of accuracy. The largest one that seems to be the first one. Actually, the first one, 32. So units is 120. Hidden activation, ReLU. Activation, we used soft, SME, atom, 1030, and then the accuracy is 32.09, which was interesting. But yeah, and that's it.